Here is the flow over a plate. The flow is two-dimensional and laminar. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present. In the narrow boundary layer region adjacent to the plate, the shearing forces and inertia forces are of equal importance in determining the motion of fluid elements. Outside of this region, the shear stress can be neglected. The thickness of the boundary layer increases along the length of the plate. Fluid deceleration is transferred from one fluid layer to another by viscosity. Moving the camera with the free stream velocity will give a better view of the boundary layer growth. The velocity throughout the boundary layer is less than that in the free stream. There is no slip between the plate and the layer of fluid immediately adjacent to it. At the plate, the relative velocity is zero. This is the no-slip boundary condition of viscous flow. The displacement of the bubbles corresponds closely to the velocity profile in the boundary layer. The thickness of a boundary layer is sometimes defined as the distance delta from the surface to where the velocity u reaches some fixed percentage of the free stream value. For our purpose, we will use 95% of the free stream velocity to define the thickness of our boundary layer. Upstream, the velocity gradient is fairly large. Downstream, it is much less. This composite photograph compares the two velocity profiles.
No matter how thin the boundary layer may be, however, it has important effects. Skin friction drag is an example. In the laminar boundary layer, fluid mixing and viscous skin friction are low, but laminar layers are frequently unstable and result in turbulent flows, which involve much more rapid mixing, producing higher skin friction drag. Transition to turbulence occurs because the laminar boundary layer becomes unstable to some type of disturbance. Here is transition slowed by a high-speed camera. Unstable waves in the laminar flow amplify to form discrete eddies. These, in turn, produce the highly disorderly motion of turbulent flow.
Here, the exact position where growth of two-dimensional disturbances begins depends on random small-scale fluctuations in the flow, and therefore varies with time in a random way. This boundary layer around a channel bend is made turbulent by placing an obstruction in the layer upstream. The obstruction stimulates the naturally occurring processes and hastens the onset of transition. The flow here is all downstream. Removing the trip rod results in separation and backflow. Bubbles accumulate at the separation point. In this diffuser, which was used before, we have made the bottom boundary layer turbulent by inserting a trip rod upstream. The turbulent boundary layer is able to withstand the adverse pressure gradient in the diffuser, while the laminar layer along the top wall is separated, allowing reverse flow. The boundary layer on the bottom side is laminar and two-dimensional. On the top side, the boundary layer has been tripped by a wire placed well upstream. Unsteady motions in the turbulent boundary layer are three-dimensional. Some of the motions are perpendicular to the plane of view. These timelines correspond closely to the instantaneous velocity profiles for the two types of boundary layers. Superimposing a number of displacement lines enables us to obtain a mean velocity profile for the turbulent layer and the laminar layer, and at the same time gives an experimental notion as to where the fluctuations occur and how large they are in the plane of mean motion. In this photograph, we can compare mean laminar and turbulent profiles. Here is the laminar one, the turbulent one. And here they are superimposed. The velocity gradient normal to the plate is larger for the turbulent layer, and it therefore has a larger wall shear stress or drag. The circulation is the same. Distribution of vorticity in the two layers is very different. There is more vorticity near the plate in the turbulent layer. The distribution of momentum in the two layers is also different. In the turbulent layer, high momentum fluid is moved toward the plate, and low momentum fluid is moved away from the plate by unsteady, random motions. There are larger shear stresses and more momentum in the turbulent boundary layer than in the laminar layer, and the turbulent boundary layer is slightly thicker.